Let us see combination of lenses. When there are 2 or 3 or 4 lenses kept side by side in contact, what is focal length of this combination, or what is power of this combination? So if there are so many lenses kept side by side, then what we do, we put an object left a first lens and form image formed by first lens. Let it is I1. Then this I1, which is image formed by first lens, is taken as object, virtual object for second lens. Image formed by second lens behaves like virtual object for third lens. Image formed by third lens behaves like a virtual object for fourth lens, and so on. So here I am taking example of 2 lenses in contact. So let us see 2 convex lenses first, kept along same axis, coaxially placed, and how we going to find combined focal length of this lenses or combined power of this lens. Let us see lens 1 and this is lens 2. These lenses are thin lenses kept in contact. Suppose this is common axis because they are placed coaxially, and this is suppose an object O. This is incident ray on first lens L1. Now if there is no second lens, then this ray would have gone like this and meet principal axis somewhere here. So this is image formed by first lens. Here, though these lenses are thin lenses, so I am measuring all distance from here. So distance of object from this lens or distance of object from this lens, we can take same. So let this is C. So this distance is object distance, and this distance is image distance formed by first lens. Now when this ray incident on second ray, it further converges, and does it follow this path? So after conversion, let it follow this path. So this is position of final image. So for second lens, this is image and this is object. So this distance I am taking as V, distance of final image from point C. So if I use refraction through first lens L1, refraction through lens L1, what we have to use, 1 upon V1, this is image distance for first lens, minus 1 upon U, object distance, is equal to 1 upon F1, focal length of first lens. Now for second lens, I1 is object, so V1 is object distance, and I is image, so V is the image distance. So for second lens, for L2, 1 upon V minus 1 upon V1, this is object distance for first lens, is equal to 1 upon F2. So this is equation for second lens. Here in theory, you may write first point, both lenses are placed coaxially and both lenses are in contact. Then let image formed by first lens is I1, which is V1 distance away from the lens. This image formed by first lens behaves like object for second lens, and image formed by second lens is I. So that is final image. Now adding these 2 equations, adding equation 1 and equation 2. So it is 1 upon V1 minus 1 upon U plus 1 upon V minus 1 upon V1 is equal to 1 upon F1 plus 1 upon F2. Now this and this get cancelled. So I'm writing first this minus this. 1 upon V minus 1 upon U is 1 upon F1 plus 1 upon F2. Let this equation be 3. Now if I replace these two lenses by a single lens, so that the single lens forms image of this object at this position at V distance, and object distance is U. Then focal length of the single lens, or you can say the single lens behaves like these two lenses. So this is equivalent length of these two. So focal length of this is, I can write from thin lens formula, 1 upon V minus 1 upon U is 1 upon F. So this is equation 4. Now from equation 4 and equation 3, if I compare left hand side, both are same. So right hand side should be same. So comparing equation 3 and 4, from equation 3 and 4, we can write 1 upon F equal to 1 upon F1 plus 1 upon F2. So F is equivalent focal length of these two lenses. So this is the formula. When two convex lenses are kept in contact, you can replace the two convex lenses by a single convex lens whose focal length equal to this, or power of combined lens or equivalent lens is equal to sum of power of the two lenses. So remember this formula. So when two lenses are in contact, this is the formula for effective focal length. Means you can replace the two lenses by a single lens whose focal length you have to take this, and this you can calculate by using this expression. Similarly, power of equivalent lens you can calculate by simply adding power of these two lenses, algebraic sum of power of these two lenses. Now what is magnification produce in this case? Magnification for lens L1, let magnification be M1. So it is I1 upon object distance. This is magnification for lens, first lens. So I1, size of image formed by first lens, is object size into M1. Now for lens 2, magnification is M2. This is size of image upon size of object. This is I1, because for second lens this is object and this is image. So size of image upon size of object. M2 is I upon I1, and at place of I1 we can write O into M1. So if I write it like this, I'm moving M1 on this side. M1 into M2 is final size of final image upon size of object. This is total magnification. Total magnification is size of final image upon size of object. This is total magnification. If I compare these two equations, the left hand side is same, so we can equate right hand side. So total magnification produced by the combination is product of magnification produced by individual lenses. So this is the formula for magnification. So why we use combination of lenses? In order to get higher magnification, because if you put 3 lenses, magnification will be m1 into m2 into m3. If you put 4 lenses, magnification will be m1 into m2 into m3 into m4. So larger number of lenses used, greater will be magnification. So sometime we need large magnification. Single lens cannot produce that magnification. For this purpose we use multiple lenses. And second advantage of using multiple lenses is, by a single lens we can get aberration in image formation. Aberration in image formation can be removed by using 2 or more than 2 lenses. So aberration or defect in image formation can be minimized by taking more than 1 lens together, one advantage, and by taking more than 1 lens we can get higher magnification. This is second advantage. So these are the 2 main advantages of having more lenses in contact. Combination of lenses, when one lens is convex and other concave. When one lens is convex and other lens is concave. Suppose this is first lens and this is second lens. First lens has focal length f1, second lens has focal length f2, and they are placed coaxially, so their axes are common. We can use same formula in this case also. Power of combination is equal to algebraic sum of power of individual lenses. Individual lens. It means we can write power equivalent is equal to power of first lens plus power of second lens. And we know that power of convex lens is positive, power of concave lens is negative. So here we have to put power of second lens negative. So it is effective or equivalent power is P1 minus P2. Now power is 1 upon focal length, it is 1 upon f1 minus 1 upon f2. So this is effective focal length or equivalent focal length. We can write this focal length as f1 f2 upon f2 minus f1. So these are the 2 expressions of focal length when one lens is convex and other is concave. Now from here 3 cases are possible. First, if f2 is greater than f1, means numerical value of focal length of second lens is greater than numerical value of focal length of first lens, then f2 minus f1 will be positive. Hence this will be positive. Then f is positive. It means this system of lenses behaves like convex lens. It means you have to replace these 2 lenses by a single convex lens whose focal length is equal to capital F. If f2 is lesser than f1, if f2 is lesser than f1 means numerical value of f2 is lesser than numerical value of f1, then this will be negative. So this focal length will be negative. It means system will behave like concave lens. So you have to replace these 2 lenses and you have to take a single concave lens whose focal length equal to f. And third case, if f2 is equal to f1, then this is infinite. f2 minus f1 will be 0. Anything divided by 0 is infinite. Focal length becomes infinite, means it behaves like a plain glass slab. Behaves like a glass slab, means it doesn't has power to bend light, so light will not be bended, means incident and final emergent ray will be parallel to each other. So that is the combination of lenses. When two lenses in contact, either they are both are convex or one concave one convex,